So y'all, Darrell Lee Bever Jr. here. We'll be doing some classical dynamics. Plan on reading through chapter 2 and chapter 3 of my textbook Classical Dynamics over the next week. So that we should be through with the 2 chapters by, let's say, Sunday of next week. So over 8 days. So stay tuned. It'll be going, I guess, relatively fast. The chapters are not too big, but still a lot of material. And so we'll be starting with the first page of chapter 2 and going from there. And we'll see how this goes. You could join the Discord with the link at the top of the screen. I am in the Discord now. So you'll be able to talk to me live if you'd like to have a chat there. As well as you can reply in the live chat if you're here. You can also ask a question in the comments on the video, and we'll see how that goes. So make one adjustment to my setup here. There we go. So go ahead and join the Discord if you would like, and be aware that I do offer tutoring. So if you like some tutoring in physics, math, or astronomy, let me know, and I can help get you right up into generally the junior level college, university. And so let's go ahead and get this party started. So chapter 2 is basically about Newtonian mechanics of a single particle. Introduction. The science of mechanics seeks to provide a precise and consistent description of the dynamics of particles and systems of particles. That is, a set of physical laws mathematically describing the motions of bodies and aggregates of bodies. Right? So mechanics, precise and consistent description. So physical laws mathematically describing motions of bodies. The motions refers to the dynamics. This, we need certain fundamental concepts such as distance and time. The combination of these concepts of distance and time allows us to define velocity and acceleration of a particle. So x being position, dx over dt, change of position over change in time is velocity. And dx over dt squared equals acceleration, meters per second squared. So the position over per second per second. Third fundamental concept, mass, requires some elaboration, which we give when we discuss Newton's laws. Physical laws must be given based upon experimental fact. We cannot expect a priori that the gravitational attraction between two bodies must vary exactly as the inverse square of the distance between them. So physical laws are empirically based. The experiment indicates that this is so. Once a set of experimental data has been correlated and a postulate has been formulated regarding the phenomena to which the data refer, then various implications can be worked out. If these implications are all verified by experiment, we believe that the postulate is generally true. The postulate then assumes that the status of a physical law. If some of the experiments disagree with the predictions of the law, the theory must be modified to be consistent with the facts. Right? That's pretty much still calculated here. Physical laws are empirically based. Newton provided us with the fundamental laws of mechanics, which are the physical laws mathematically describing the motions or the dynamics of bodies, including systems of bodies. We state these laws here in modern terms, discuss their meaning, and then derive the implications of the laws in various situations. But the logical structure of the science of mechanics is not straightforward. Our line of reasoning in interpreting Newton's laws is not the only one possible. We do not pursue in any detail the philosophy of mechanics, but rather give only sufficient elaboration of Newton's laws to allow us to continue the discussion of classical dynamics. We devote our attention in this chapter to the motion of a single particle, leaving systems of particles to be discussed in chapters 9, 11, 12, and 13. Now we're in section 2.2, so that was 2.1. Intro. 2.2, Newton's laws. We begin by simply stating the conventional form Newton's. We begin by stating in conventional form Newton's laws of mechanics. 1. A body remains at rest or in uniform motion unless acted upon by a force. So, motion or still unless acted by a force. 2. A body acted upon by a force moves in such a manner that the time rate of change of momentum equals the force. The time rate of change of momentum. So the actual law is F equals dp over dt, which equals d over dt p, which equals d over dt mv, which equals m d over dt v, which equals ma. So that's how we get our how we normally say it, acceleration, with the actual form as Newton said it is momentum, which stands to reason it will be a little bit extra. But we don't normally deal with momentum, I guess, when we're calculating the motion and position of something. If two bodies exert forces on each other, these forces are equal in magnitude and opposite in direction. 3. F equal opposite. These laws are so familiar that we sometimes tend to lose sight of their true significance, or lack of it, as physical laws. Here. first law, for example, is meaningless without the concept of force, a word Newton used in all three laws. In fact, standing alone, the first law conveys the precise meaning only for zero force. That is, the body remains at rest or uniform, unaccelerated or rectilinear motion. The body remaining at rest or uniform motion, unaccelerated rectilinear motion, is subject to no force whatsoever. A body moving in this manner is termed a free body or free particle. The question of the frame of reference with respect to which the uniform motion is to be measured is discussed in the following section. In pointing out the lack of content of Newton's first law, Sir Arthur Eddington observed somewhat facetiously that all the law actually says is that every particle continues in a state of rest or uniform motion in a straight line, except insofar as it doesn't. This is hardly fair to Newton, who meant something very different by his statement, but it does emphasize that the first law by itself provides us with only a qualitative notion of regarding force. The second law provides an explicit statement. Force is related to the time rate of change of momentum. Newton appropriately defined momentum, although he used the term quantity of motion to be the product of mass and velocity, such that, as I showed there, P equals mv. This is equation 2.1, or P, I guess, is defined as mv. Therefore, Newton's second law can be expressed as, and actually this is what I have here, F equals dp over dt, which equals eventually d dt of mv, which equals ma. The definition of force becomes complete and precise only when a mass is defined. Thus, the first and second laws are not really laws in the usual sense. Rather, they may be considered definitions. Because length, time, and mass are concepts normally already understood, we use Newton's first law and second law as the operational definition of force. Newton's third law, however, is indeed a law. It is a statement concerning the real physical world and contains all of the physics in Newton's laws of motion. We must hasten to add, however, that the third law is not a general law of nature. The law does apply when the force exerted by one point object on another point object is directed along the line connecting the objects. Thus, forces are called central forces. So central forces central force is F directed along line of central mass to objects. The third law applies whether a central force is attractive or repulsive. Gravitational and electrostatic forces are central forces. So Newton's laws can be used in problems involving these types of forces. Sometimes elastic forces, which are usually macroscopic manifestations of microscopic electrostatic forces, are central. For example, two-point objects connected by a straight spring or elastic string are subject to forces that obey the third law. Any force that depends on the velocities of the interacting bodies is non-central. Any forces that depends on the velocities of the interacting bodies is non-central, and the third law may not apply. If F depends on V, non-central. The third law may not apply. Right, so keep that in mind. Velocity-dependent forces are characteristic of interactions that propagate with finite velocity. Thus, the force between moving electric charges does not obey the third law. between moving electric charges. Right? Well, we know a moving charge creates a field, a magnetic field. If I remember right, I should know that, I think. I can't remember exactly, but we know that a moving charge does something extra. Yeah, moving charges makes a magnetic field. It's like our when a current through a wire makes a magnetic field around the wire. So maybe that's something to do with why the moving charge is slightly different. Because the force propagates with the velocity of light. The force between moving electric charges does not obey the third law because the force propagates with the velocity of light. Even the gravitational force moving between bodies is velocity dependent, but the effect is small and difficult to detect. The only observable effect is the projection of the perihelion of inner planets. We will return to a discussion of Newton's third law in Chapter 9. To demonstrate the significance of Newton's third law, let us paraphrase it in the following way, which incorporates the appropriate definition of mass. If two bodies constitute an ideal, isolated system, then the acceleration of these bodies are always in opposite directions, and the ratio of the magnitudes of the accelerations is constant. This constant ratio is the inverse ratio for the masses of the bodies. All right. So basically, F equals ma, and if we have two bodies acting on each other, F1 would be opposite F2. So we can say ma equals negative ma. So this means that the ratio uh, A1 over A2 will equal negative m over m. The ratio of the magnitudes of accelerations is constant. This constant ratio is the inverse ratio of the masses of the bodies. Right? So this is what they mean. This will be m1, this will be m2. So the inverse ratio of the masses equals the ratio of the accelerations. So this is what it means by that. The ratio of the magnitudes of the acceleration is constant. This constant acceleration ratio is the inverse ratio of the masses of the bodies. Right? That's a very complicated way of just saying this simple thing. But we have two bodies that are acting upon each other. We know that we can equate the masses and say that the mass 2 divided by mass 1 equals acceleration 1 divided by acceleration 2. And we know acceleration 2 is going to be less because it has to equal the larger mass, and which makes sense. F equals ma, the larger the mass, the smaller the acceleration, because the same amount of force will be on the larger mass, but since it has a larger mass, it's not going to move as much. With this statement, we can give a practical definition of mass and therefore give precise meaning to the equations summarizing Newtonian dynamics. For two isolated bodies, 1 and 2, the third law states that F1 equals negative F2, which is exactly what I wrote here. Using the definition of force as given in the second law, we have dp1 dt equals negative dp2 dt, with constant masses. m1 dv1 dt equals m2 dv2 dt with a minus. And because acceleration is the time derivative of velocity, m1 a1 equals negative m2 a2. This is what they have is equation 2.4c. Hence, m2 m1 equals negative a1 over a2. So but they put the negative on the other uh, 2, which makes sense. I guess mass will never be negative, but that's okay. Where the negative sign indicates only that the two acceleration velocities are oppositely directed. So why don't I change that? And this means that the two acceleration velocities are oppositely directed. Because one acceleration divided by another acceleration is negative. So that means they're going in different directions. One is in the negative x-axis, one is in the positive x-axis, for instance. Mass is taken to be a positive quantity, right? So it's important that we do have the negative on the proper thing. The negative always follows the velocity acceleration position. We always select, say, m1 as the unit mass. Then by comparing the ratio of accelerations when m1 is allowed to interact with any other body, we can determine the mass of the other body. In other words, m1 is given, or I should say known. m1 equals known. So m1 interacting with m2 allows termination of m2 from acceleration. So this is the working definition of mass. Mass is what the property of matter that maintains this ratio of acceleration when these two masses interact. The mass is defined in a sense by acceleration in mechanics. The practical definition of mass. We see that the practical definition of mass is defined by acceleration, the acceleration of two masses in relation to each other, given one mass is established and known. To determine the accelerations, we must have appropriate clocks and measurement rods. Also, we must choose a suitable coordinate system or reference frame. The question of a suitable reference frame is discussed in the next section. One of the more common methods of determining the mass of an object is by weighing. For example, by comparing its weight to that of a standard by means of a beam balance. This procedure makes use of the fact that in a gravitational field, the weight of a body is just a gravitational force acting on the body. That is, Newton's equation F equals ma becomes weight equals mg, weight. Where g is the acceleration due to gravity. The validity of using this procedure rests on the fundamental assumption that the mass m appearing in Newton's equation and defined according to statement 3 is equal to the mass m that appears in the gravitational force equation. The two masses are called the inertial mass and the gravitational mass respectively. The definitions may be stated as follows. All right? So inertial mass the mass determining acceleration. Gravitational mass. The mass determining Fg, gravitational forces between a body and other masses. Galileo was the first to test the equivalence of inertial and gravitational mass in his perhaps apocryphal. Let's see what they mean by apocryphal. They're not really sure it's true, might be fictitious. Apocryphal experiment with falling weights at the Tower of Pisa. Newton also considered the problem and measured the periods of pendula of equal lengths but with bobs of different material. Neither Newton nor Galileo found any difference, but the methods were quite crude. In 1890, Ch2 devised an ingenious method to test the equivalence of inertial and gravitational masses. Using two objects made of different materials, he compared the effect of the Earth's gravitational force, the weight, with the effect of the inertial force caused by the Earth's rotation. The experiment involved a null method using a sensitive torsion balance and was therefore highly accurate. More recent experiments, notably those of Dick, using essentially the same method, have improved the accuracy. And we know now that inertial and gravitational masses are identical within a few parts in 10 to the 12. This result is considerably important in the general theory of relativity. So apparently I'm going to learn about this later if I can take that class. Relativity is a class I wanted to take, but I don't think it'll be available next spring. I'll take a look and see if I can find that right now. It looks like it is too early to see the 2025 one, but this is still possible. I don't think it was planned, but plans do change, right? I guess I got to look up this experiment. I'm not sure what would have happened, but Ch2, his name is spelled E-O with two dots, T-V-O with two dots, S. So in 1890, E-O two dots, T-V-O two dots, S. Devotes portion balance. So um, I'll see if I can find this paper somewhere. it- So I did find a paper, 100 years of the Yodfos experiment, but I may just come back and read that another time. The paper from 1991. Perhaps they'll have a reference to the actual paper. Um, but that's good for now. Let's go back to the text. And I'll continue, I guess, until about 12:30, I guess. Somewhere around there, 12:30. And I'll be back. So I plan on reading this all day. See if I can get through 2 chapters this week. Hopefully I can get through it in a few days. The assertion of the exact quality of inertial and gravitational mass is termed the principle of equivalence. Principle of equivalence. So gravitational mass is the same as inertial mass. In other words, if I have a mass times the gravity of a larger mass like the Earth, I'll get a weight value. And that weight value will be consistent with the force of acceleration. For instance, with that mass with another mass. So that same mass, that value for mass is the same in both realms of motion or dynamics versus a static force. Newton's third law is stated in terms of two bodies that constitute an isolated system. It is impossible to achieve such an ideal condition. Every body in the universe interacts with every other body, although the force of interaction may be far too weak to be of any practical importance if great distances are involved. Newton avoided the question of how to disentangle the desired effects from all the extraneous effects. Newton avoided the question of how to disentangle the desired effects from all the extraneous effects. But this practical difficulty only emphasizes the enormity of Newton's assertion made in the third law. It is a tribute to the depth of his perception and physical insight that the conclusion, based on limited observations, has successfully borne the test of experiment for 300 years. Only within the 20th century did measurements of sufficient detail reveal certain discrepancies with the predictions of Newtonian theory. Pursuit of these details led to the development of relativity theory and quantum mechanics. Another interpretation of Newton's third law is based on the concept of momentum. Rearranging equation 2.48 gives this is what they're saying for the third one. They're saying d over dt of momentum 1 plus momentum 2 equals 0. And this is because one of them is negative. So this is to say d over dt m1v1 plus m2v2 equals 0. So m1a1 plus m2a2 equals 0. So m1a1 equals negative m2a2. And then we get back to where we were before. m1a1 equals negative m2a2. f1 equals f2, negative f2, right? So p1 plus p2 equals constant. And of course, 0 is a constant number. All right. The statement that momentum is conserved in the isolated interaction of two particles is a special case of the more general conservation of linear momentum. Physicists cherish general conservation laws, and the conservation of linear momentum is believed always to be obeyed. Later, we shall modify our definition of momentum from equation 2.1 for high velocities approaching the speed of light. And P equals mv is 2.1. Okay, so that's the end of that section. That's pretty good. Frames of reference. Two point three. We need to realize that for the laws of motion to have meaning, the motion of bodies must be measured relative to some reference frame. A reference frame is called an inertial frame, and Newton's laws are indeed valid in that frame. So an inertial reference frame laws are valid in that frame. That is, if a body subject to no external force moves in a straight line with constant velocity or remains at rest in the coordinate system, and establishing this fact is an inertial frame of reference. All right. So we can measure the Newton's laws hold if the reference frame that we have shows that working according to Newton's laws, then the frame that we're using to show that interaction is an inertial frame. This is a clear-cut operational definition and one that also follows from the general theory of relativity. If Newton's laws are valid in one reference frame, then they are also valid in any reference frame in uniform motion, i.e. not accelerated, with respect to the first frame. This is a result of the fact that the equation F equals mr double dot involves the second time derivative of r. A change of coordinates involving a constant velocity does not influence the equation. This result is called Galilean invariance, or the principle of Newtonian relativity. Relativity theory has shown us that the concepts of absolute rest and an absolute inertial reference frame are meaningless. Therefore, even though we conventionally adopt a reference frame described with respect to the fixed stars, fixed as in quotes, and indeed in such a frame the Newtonian equations are valid to a higher degree of accuracy, such a frame is, in fact, not an absolute inertial frame. We may, however, consider the fixed stars to define a reference frame that approximates an absolute inertial frame to an extent quite sufficient for our present purposes. Although the fixed star reference frame is a conveniently definable system and one suitable for many purposes, we must emphasize that the fundamental definition of an inertial frame makes no mention of stars, fixed or otherwise. If a body subject to no force moves with constant velocity in a certain coordinate system, that coordinate system is by definition an inertial frame. Because precisely describing the motion of a real physical object in the real physical world is normally difficult, we usually resort to idealizations and approximations of varying degrees. We ordinarily neglect the lesser forces in our body if these forces do not significantly affect the body's motion. If we wish to describe the motion of, say, a free particle, and if we choose for this purpose some coordinate system in an inertial frame, then we require that the vector equation of motion of the particle be independent of the position of the origin of the coordinate system and independent of its orientation in space. We further require that time be homogeneous, that is, a free particle moving with a certain constant velocity in the coordinate system during a certain time interval must not, during a later time interval, be found to move with a different velocity. Given that the velocity is constant. We can illustrate the importance of these properties by the following example. Consider, as in figure 2-1, a free particle moving along a certain path AC. To describe the particle's motion, and we'll take a look at this here. And let me adjust the positioning of this thing. Right? So we can illustrate the importance of these properties by the following example. Consider, as in figure 2.1, a free particle moving along a certain path AC. And this is figure 2.1 here. You see the path AC up top. You can keep that image in mind. We'll come back to it. To describe the particle's motion, let us choose a rectangular coordinate system whose origin moves in a circle as shown. For simplicity, let the orientation of the axis be fixed in space. Particle moves with velocity Vp relative to the inertial reference frame. So the origin of the coordinate system is moving. If the coordinate system moves with a linear velocity Vc when at the point B, and if Vc equals Vp, then the observer in the moving coordinate system of the particle at A will appear to be at rest. At some later time, however, when the particle is at C and the coordinate system is at D, the particle will appear to accelerate with respect to the observer. We must therefore conclude that the rotating coordinate system does not qualify as an inertial reference frame. Right? So at A and B, the particle and the person observing it are moving in the same direction at the same velocity. Therefore, the particle will appear to be at rest. When the person is moving in the opposite direction from the particle will appear to be accelerating. Well, I guess not accelerating on the opposite side here, but at D, the particle and the uh, uh, person observing are moving, at least the person is changing direction. Therefore, the particle will seem to be speeding up, but really it's the observer changing direction, and the velocity is starting to go more in a direction away from the particle as the particle continues to move. So ironically, they're both going at constant speeds, but the change in direction in D causes it to seem like an acceleration. And technically, it is an acceleration because the velocity is changing direction, but the motion around the circle is constant velocity. So therefore, the reference frame at the bottom is not an inertial reference frame. And it is obviously accelerating. Right. Let's go back to the hand notes. These observations are not sufficient to decide whether time is homogeneous. To reach such a conclusion, repeated measurements must be made in identical situations at various times. Identical results would indicate the homogeneity of time. Repeated measurements in identical situations at various times determines the homogeneity of time. Newton's equations do not describe the motion of bodies in non-inertial systems. We can devise a method to describe the motion of a particle by a rotating coordinate system, but as we shall see in chapter 10, the resulting equations contain several terms that do not appear in the simple Newtonian equation F equals ma. For the moment, then, we restrict our attention to inertial reference frames to describe the dynamics of a particle, the motions of a particle. Right. So why don't I take a brief break, and then I'll be back in a few minutes. I'll leave you all with my intro page and some music for the time being. All right, you all, back after a quick break, and we shall continue with where we were. So, and I'll do one more thing. It's actually pretty warm up in here, and because they're getting ready for winter. I'll go short sleeved, and we'll continue, right? Now we're in section 2.4. 2.4, we created a motion for a particle. Use equation F equals v over dt T can be expressed alternatively as minus 2.7 if we assume that the mass m does not vary with time. This is a second order differential equation that may be integrated to find r equals rt if the function f is known. In other words, m r double dot equals f. If we know f, we can integrate this thing. And I demonstrated, actually I could show this now. And this will actually be equals ma. So we can say, and this is double dot, we can say r dot plus p equals at plus r dot not. And then we can say, if we integrate this, we can say RC equals AC2 2 plus R dot not C plus R not. And in this case, R dot equals dr dot over dt, and R dot equals dr over dt. And we just divide the dt to the other side and have that worked out. Right? Easy enough. I did a shorthand of this. Maybe I'll take more time and do it fully the next time, fully describing the differential fractions. Let's keep going. But we'll assume the mass m does not vary with time. We did an integration of f is known, specifying the initial values of r and r dot equals v, then allows us to evaluate two arbitrary constants of integration. So that would be these two constants here, r dot and just regular r naught. Specifying the initial values of r and r dot equals v, then allows us to evaluate the two arbitrary constants of integration. We then determine the motion of a particle by the force function f and the initial values of position r and velocity. The force F may be a function of any combination of position, velocity, and time, and is generally denoted as FRVT. For a given dynamic system, okay, familiar with that idea, but we'll keep going. For a given dynamic system, we normally want to know R and V as a function of time. Solving the equation 2.7, and they're calling this one 2.7, will help us do this by solving for R double dot. Applying equation 2.7 to physical situations is an important part of mechanics. And we do this a lot. In this chapter, we examine several examples in which the force function is known. We begin by looking at simple force functions, either constant or dependent on only one of R, V, or T, and only one spatial dimension as a refresher of earlier physics courses. It is important to form good habits in problem solving. Here are some useful problem solving techniques. One, make a sketch of the problem, indicating forces, velocities, and so forth. Sketch with forces, velocities, etc. Write down given quantities. And 3, write down useful equations and what is to be determined. Write equations. And 4, write sought. Write what we're trying to find. 5, strategy and the principles of physics must be used to manipulate the equations to find the quantities sought. Algebraic manipulations as well as differentiation and integration is usually required. Sometimes numerical calculations using a computer are the easiest, if not only, method of solution. Strategize with algebra, integration, etc. And 6, finally put in the actual values for the assumed variable names to determine the quantity sought. Lastly, input values and solve. All right? So this is a good place to stop. We'll continue here next time. We're on page 55. Thank you all for joining and watching. Those who join and watch later, make sure you comment, like, subscribe if you haven't already. And I'll be back after lunch, and we shall continue going through this book with the goal to go through chapter 2 and 3 within the next week. So I'll see you next time later today.